Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This is episode 53, which I called TAA on wax. By the way, I'm slightly translucent. There's a tiny bit of sunshine coming in the window. Summer's almost here. Pretty stoked about that. Alkama, thank you so much for the sub, by the way. That's a great way to start the stream. Anyway, today is going to be a little bit different. What I've been working on lately. So, I didn't stream last week, did I? No, I didn't. And the week before, I was working on some Node stuff. I've been working on a lot of stuff since revision. And a lot of it's been for several reasons. One of them is that I'm going on vacation for about 2.5 weeks. And I'm really sorry that I didn't announce that because I just forgot amidst all the things that I'm doing. All the things that I want to do before we leave so that I'm not thinking about them on my vacation. That's why I bring that up. So I won't be streaming during that period. And in the meantime, I've been working on Node system for our demo tool, but I haven't really touched that since the last stream. I've been working on temporal anti-aliasing, at least trying it out in our renderer, and so far I think that's going really well. I'll go over that in quite a lot of detail in a little bit. And in fact, before I show that, I kind of want to show without it and kind of highlight some of the problems we're trying to fix before I really dive into that. Actually, that's the major things. And just a lot of other life stuff, I guess. Yeah. Anyway, why don't I just dive into this? Not waste any time, because the last night I really have to work on anything before I leave. Yeah, so anyway, Dope on Wax, the intro we released at Revision this year. We got first place. I'm pretty happy with that. However, there are some things in the intro that I'm not, mostly tech-wise. I mean, there's a lot of artistic things that I would like to change as well, but one of the things that I knew that I wanted to fix was the anti-aliasing. Let me show you what aliasing is. I mean, I'm sure most of my audience kind of knows what these problems are, but just so you're not aware. So this is the demo as it was released. And for the most part, this looks pretty good, but even in a scene like this, already in the very first shot, you can see a lot of flickering. And obviously this kind of ruins the illusion. A lot of flickering here, a lot of flickering here. The main issue here is that we have a lot of these like shiny and reflective materials. But only so much resolution. Only so much resolution to render that in terms of how many pixels we have. So we're essentially undersampling a really high frequency signal. And whenever you do that, you get aliasing, whether it's in images or audio or whatever. If you're sampling a signal and you don't have enough resolution to do it, you get signals with frequencies above the Nyquist, and you get this kind of flickering. So that's kind of the main issue is we call this temporal instability because over time it's flickery, which is sort of a way to describe sort of the consequences of doing this a bit poorly. By the way, hi guys in the chat. I'm a little distracted right now, but we'll get on track as we go along here. Zakwar, Reconstructor, Garrett Kelly, Alkama, Moliv, Mad Moose there in the German. Pro Scion. Good to see you guys. Mr. Tobe, how's it going? Mad Moose says, or make it flicker more, lean into your flaws. A lot of demos do that. I really like that. Philadelphia. Oh, thanks for the follow, Weird Constructor. But yeah, so essentially it's noise over the range of a sample. I can actually draw essentially what's happening here. Imagine we have this signal that's like spiky. But of course we're trying to render this with pixels. So if we rendered pixels and we just like tried to snap this pixel somewhere, we might get a pixel here and a pixel here, in which case we've actually totally missed the signal. We might get a pixel here and a pixel here. So depending on like where this signal was placed in relation to our pixels. So in this case, this pixel is going to be really bright and these pixels are going to be a lot darker. And if this were to move over time, especially slowly, we're going to have a lot of flickering as this sort of moves between pixels. So in this, it'll be here, and then it'll be here. And there's a lot of ways to get around this. We'll go over a couple today, mostly the relevant ones, just to give enough context for what we're doing here. Systems theory and signal processing. I have a really terrible DSP knowledge. It's way too light. That's something I would like to improve. But anyway, this is like the most basic understanding or the most basic explanation I think I can give about aliasing in general. Yeah, again, there's a bit more light coming in than normal, and I'm just not going to deal with it because I want to be spoopy today. No, it's because I just don't want to deal with it. Anyway. So that's essentially what the problem is. And aliasing in this case kind of comes in like two flavors. One of them is that flickering over time. The other one is you get hard edges. And so right now we kind of actually solve the latter case with something called FXAA. So essentially there are a lot of ways to solve aliasing in a general sense. One of them is to not have signals that have such high frequencies that this could happen. And if you're talking about band limited oscillators, that's exactly what they're doing in audio. They will generate frequencies. So typically if you have like a sawtooth or a square wave, which was represented something like this, you can't actually represent these instantaneous changes accurately. So typically you'll want to do a version of the square wave with all the frequencies up until half your sampling rate, which we call the Nyquist. Really don't need to know most of this, but you represent a square wave up until that. So actually you want something that's a little bit like this is what it would look like for your square wave. And this is just because if you break down a signal, it can be represented by a sum of sine waves. And if you remove all the sine waves that are higher than a certain frequency, then you have what we call band limiting. We do a little bit of this in Wavesaber, for example. It sounds a lot better than not doing this. You can also think of removing those high frequencies as a blur, which is exactly what Procyon said. And Aaron the German as well. So yeah, image low pass, exactly the same kind of stuff. We're removing those high frequencies. So that's like one way that you can do it. And when we're talking about graphics, there's a few different ways that happens. For example, in an image, you can have aliasing from a few different places. One of them is if we're drawing a bunch of triangles, for example, you might have aliasing along the edges of these triangles because the edge here represents just sort of like a mathematical bound where on one side you're in the triangle, on the other side you're not. And the edge here actually would move very smoothly if you move the vertices really smoothly. But if you end up like snapping the vertices to pixel positions, or if you're doing like OpenGL or something, it will snap the individual pixels of the triangle to like you either are drawing or you aren't. I'm ignoring MSAA right now, but we'll get to that. Then you're going to get this kind of aliasing as well, where like the edge is kind of going to crawl across pixels a little bit, and you get stair stepping kind of thing. And so one of the ways you can do that is you can blur all the edges of your triangle, and that's what like MSAA does. They say, okay, for every pixel, we have the actual edge, and we're going to see how much of this pixel is actually covered by this edge. And we're going to use that to essentially say whatever the color would have been for this pixel had we taken the whole pixel, but we're only going to apply it with blending based on how much is actually covered by the edge. Multi-sample anti-aliasing, that's called. So you're essentially multi-sampling this at the edge, and then, yeah. I'm going to hand wave a lot here because I don't think it's actually terribly important to understand a lot of these other techniques, but it's just one of the ways you can deal with this. That covers a lot of your edges or aliasing from edges of triangles, but of course there are lots of other places that this can happen. So I mentioned earlier, like there could be spikes in your signal here. So let's say this triangle happened to be normal mapped, and so there was a lot of bumps on here. And some of those bumps would be really shiny for a pixel, and then some of those wouldn't be. And we would call this shader aliasing, or specular aliasing. But the point is that there's a noisy signal that can't properly be represented with the pixels. And MSAA, for example, like this kind of coverage thing can't help you because that's only going to happen at the edge of the triangles. So in that case, you might want to look at other ways of doing this. A lot of renderers nowadays are doing what's called deferred rendering, and our renderer, for the most part, has been doing that as well. In fact, I actually don't think we've done a demo that didn't do deferred rendering except for IOTA, since we've been doing Logicoma demos at least. So yeah, I think most of them have been using deferred renders. And our latest renderer that we've been using in Trash Panda and Dope on Wax is definitely doing a deferred rendering. And what you do there is, instead of actually drawing and shading, drawing shaded triangles to the screen, you have several passes. So initial pass will draw out to a bunch of buffers. So instead of writing a triangle to a color buffer, you say, okay, I'm going to have a normal buffer and a depth buffer and a position buffer, whatever buffers you need. We're actually a bit wasteful on which buffers that we use because it just makes it a little more convenient, and we have enough bandwidth on a high-end PC to just be a little bit sloppy with that. So what you do is, instead of drawing a triangle like as color, you draw, here's all the normals for all the pixels in one buffer, and here's all the depths in another buffer. And then what you'll do is you'll sort of draw in the lights as sort of, here's the pixel area that light covered. And then based on what was in those, what we call G buffers, those other buffers of positions and normals and all that stuff, then you'll calculate the lighting there. And there's a lot of reasons you might do this. Yeah, Okama says, and you cry about transparency. Yes, I'm going to not talk about that at all. Transparency, volumetrics, all this stuff kind of suffers. But there's some really nice ways, or nice benefits to doing this. The main one in our case is that things are a little bit more composable. You don't have like big long shaders that have a lot of special cases. You just have your shaders that draw to the G buffers, because we have other buffers here with like material parameters. And then you have shaders that represent lights, so they're like completely separate, where the light shaders will just pull in all the information that they need from the G buffers and then do whatever they need to do with additive blending. It just kind of works out. So again, where I like to play around a lot with like adding and removing lights and all this other stuff, it's just a lot easier to do with a deferred renderer. But of course, deferred renderers have this property where you can't do this edge anti-aliasing because you've thrown out all of your edges by the time you actually wrote to the frame buffer. But that's not really a good enough solution for us anyway, because we have a lot of potential shader aliasing. So what a lot of other techniques will do is sort of a post-processing pass. And that's where you sort of already write out an aliased image, and then you sort of do anti-aliasing on top of that, where you kind of try to blur out smooth edges or something. Smooth out sharp edges. That's what you want to do. So the technique that we've been using since 2016 is called FXAA, which is fast approximate anti-aliasing. And what it does is it's a pure image space operation. So you get an aliased image in with all your stair stepping. I drew Canada. And then and then what you'll get is a smoother image out, which hopefully aligns with what the triangles actually were. So the way that this works is, for every pixel, essentially, we'll try and look around the image a little bit and try and find where the edge is, just looking at like color or luma differences between the pixels, and then it will figure out how far along that pixel is on that edge and then blur different pixels around accordingly. What's really nice about FXAA is it's just one shader. It's one shader, and then you have to have the pass that outputs the color before that. You need to stuff luma into the alpha channel as well for it to work. But you just like download the shader and then you put it on there and it works, and it's really fast. It's really fast. That's why it's called fast approximate anti-aliasing. So it's fast because it's just doing this simple pass. It's approximate because what you ideally would want to do is somehow represent like the subpixel information in the way that you're anti-aliasing, and that's how you would actually get a smooth edge over time. Whereas this is just approximate. This just clears up that one image, and so you actually get a lot of temporal instability with this approach. So as this edge would kind of move through pixels, since the FXAA doesn't know about like previous frames or like where the edge was in the previous frame versus where it is in the current one, these edges that it's going to find are going to be a lot different, varying between frames. So you're going to get a lot of flickering. So even though a still image might look pretty good, you're going to get a lot of flickering. And also with a lot of edges, like there could be details in this image that the FXAA couldn't find. So then there are parts that are going to be sharp that shouldn't have been sharp. And there's also the opposite case where there should have been sharp edges, but there actually won't be because the FXAA thinks it's an edge of a triangle and just starts blurring it. So there's a lot of problems with this, but the nicest thing, again, is that you can just kind of put it on the top and it solves a lot of problems. It's better than not doing anti-aliasing, generally. Weird Constructor says, why do you still work on a demo that is already done? Are you putting the work for long-term improvement of the engine or for future artistic expression? That's exactly it. So I typically will do this after we finish a demo, just kind of go in and like, what can we improve for the next one while I'm still like excited about doing graphics programming. And in this demo especially, even before we released it, like since we released it, we've gotten some feedback, of course, about how bad the aliasing was. And I knew that before we were releasing it, especially these initial shots that I showed you earlier here, this shot in particular. Like, this is so flickery. And I hate that. But at the same time, it's like, I knew that I wanted to do the scene, and I just didn't have time to look into the aliasing, what with doing the entire demo at the same time. So I knew that I wanted to look into this eventually, and I also had this temporal stuff on my radar for a while. But I knew it would be messy, and I'll talk about why it's messy when we get into that. I'm glad you found the aliasing charming. I found it distracting and annoying, and it bugged me to no end, but I just we didn't have time to fix it. Anyway, that's what I'm working on now. Yeah, I like what Alkama said, by the way, like ironing your shirts. Yeah, exactly. Like FXAA kind of tries to smooth out the wrinkles on a given frame. But yeah, it's not really going to work. Yeah, Mad Moose, actually, you raise a good point. You said render at 16x. What's the problem? So that's actually a great way to eliminate aliasing. If you have like infinite time and infinite compute, if you render your image at like 8 times or 16 times the resolution and then just downscale with a nice downscale filter, like even just collecting all the 16 by 16 samples, just averaging them, will actually work really good, and it'll have awesome temporal stability. It's going to look perfect. It'll pick up all your subpixel details. It's awesome. And that's what MSAA is trying to approximate. And I think it actually will do that on the edges of triangles. To be honest with you, I'm not actually entirely sure about the implementation details. I thought it was doing just coverage sampling and then blending, but it might actually be rendering the edges at high resolution. Either way. Yeah, I think you're right, Alkama. That's super sampled anti-aliasing, and I think MSA is just doing the coverage. Honestly, I don't remember. Anyway, my point is, those doing something in high resolution and then bringing it down is a great way to do it, because what you end up doing is you end up, essentially, if we go back to this original example, you end up actually having enough pixels to more accurately represent this signal. Just pretend I have a lot. And then when you do your downscale, because you're blending all those together, you are actually blurring this signal. You have enough information to do it accurately, but then you're blurring it to kind of get like an approximated version of it with lower sample rate, but you're doing that in a way that preserves the subpixel information. So that's really great. Exactly what Portal Science said, something Nyquist-Shannon theorem. 100%. A great way to do it. But again, the problem is that you don't have infinite compute. If you're going to render at 16 times the resolution, you need 16 squared. So 256 times the amount of pixels. I don't think you're going to have enough time to do that by the time you need to be rendering the next frame. So if you do have enough time to do that, awesome. If you're doing offline renders, not a bad way to do it at all. Of course, there are some things where you're going to be undersampling, like if you're doing some reflection stuff, you might be undersampling in other ways. MSA will help with that, of course, but yeah. Anyway, so we're not doing that. One of the things that's become popular in the last, I want to say 5 years that it's been like really popular, but it's been a little bit more than that. It's been almost 10 years, I think, that people have been really taking this technique seriously. Actually, maybe 8 years that people have been taking this technique seriously. But it's called temporal anti-aliasing, or generally there's some temporal element to it. So what you want to do is, instead of super sampling in resolution, so every pixel gets 4 pixels or 8 pixels or whatever, what you actually want to do instead is super sample in the temporal domain. So one way to do this is, for every frame, you render it 8 times. You render it 8 times with slightly different time, and then you blur all those results together. And this actually is going to give you a couple of different nice things. This would actually give you good motion blur. This would give you mostly some subpixel detail. There might not actually be any if your camera's not moving. We'll get to that. Yeah, sphere tracing also has these problems. In fact, a lot of the time sphere tracing is worse with this kind of stuff. Get a lot of temporal instability problems with sphere tracing that I wouldn't say are inherent to the algorithm, but because your GPU can't do anything clever with it, you tend to have a lot of these problems. But that's a nice thing about like FXAA as well, is that'll work on a ray-marched image, it'll work on a rasterized image, whatever you throw at it, it will do something to it that probably helps. But yeah. Anyway, so what you'd ideally do is you'd render a bunch of frames with slightly different time, and then you'd average all those together. However, as Alcama points out, that's not actually what we do, because you don't want to render the scene 8 times. It has the same problem as multisampling in the with resolution. You ideally want to instead actually just render one and then try to use some kind of history information. And so what we end up doing instead is that we have we take the previous frame and we try to sort of use that as like our history when we're doing the current frame. So we're going to render an aliased image, and we're somehow going to blend it with the previous frame, and then ideally we'll get a nice image. That's effectively what we're doing. So we're essentially saying the last frame is going to be like a history buffer, and every pixel is going to represent the history of that pixel on the screen over some time. And so typically the way that you combine these is you blend this. You say, I'm going to take 10% of the new image and combine it with 90% of the history image. And so over time, you get this sort of exponential moving average where this accumulates stuff over time, over several frames, and then that you're just feeding the new information to that all the time. This turns out to work extremely well, actually, but it's definitely not without its problems. Definitely not without its problems. Sphere tracing is a thing that people have taken seriously in the demo scene for about 10 years. Cheat detector. The girlfriend asked what that flag's supposed to show. It's supposed to show, I don't know. I'm not even going to make something up. It's supposed to show ghosting. Yes. That's. Oh, man. You guys are way ahead of the curve here. I don't need to talk about what I'm doing at all, do I? Just need to talk about the details. Anyway, there are a lot of problems with this, but let me just say first of all that if you do this and your camera doesn't move, you're actually going to get something that actually looks like the exact same image. So because you would end up rendering this exact same frame like every time, and then if you average that same frame with a history, eventually it's going to converge on that same frame again. It's going to stay there. So typically what we actually do is every frame we actually jitter the content a little bit, and that will allow these pixels in the history buffer, as they're accumulating history, to accumulate slightly different history over time. It's sort of the same thing as with like MSA when it's doing that sort of sample coverage. You're sort of, instead of checking if the pixel is within or without this edge, you're sort of moving this edge back and forth a lot. And sometimes it hits the pixel and sometimes it doesn't. Hey, Robert Al. And so over time, the amount of times that this pixel was illuminated with that edge, the amount of times it wasn't, sort of tells you how much of that edge actually covers that pixel. And that gives you a nice smooth edge with nice subpixel details over time. It's actually a really cool idea. So with that averaging and that jitter, if your camera doesn't move other than that slight jitter, and you do this averaging, you will get an awesome image. This is a great way to super sample. It's a great way to render. However, that's not all we can do, because as soon as your camera moves or any of the objects move, if you don't have a static scene, then you're going to have big problems with ghosting. And ghosting is, actually there's a really good so I'm going to pull up a lot of slides here from different people and different presentations that people have already given. This is Brian Karas's 2014 talk, High Quality Temporal Supersampling. This is about the TAA implementation in Unreal at the time. And actually, while I'm here, I can show you also. This is an image. This is the image you want to render. This is that same image with no anti-aliasing, so lots of jaggies everywhere. And this is the same image with FXAA, so still some jaggies. And this would flicker like hell. So anyway, that's kind of what we're trying to solve. Lots of stuff. Here's talking about the jittering, moving average stuff. We'll talk about that brightness stuff. Ghosting. This is what ghosting looks like. So if you're moving your camera around or you're moving the objects around and you're just doing that naive accumulation, this is what will happen because you'll see the previous frames very clearly in the history buffer here. So you need to accept pixels on an edge as you're moving around, and you also need to reject a lot of pixels because like if you move the camera, you want to sort of have, let me sort of draw this in a nice way. Let's say this is frame A. We have a sphere here. And in frame B, we either move the camera or we move the sphere. Ignore the aspect ratio change. That's not important. Sphere moved to here. So when we're accumulating all the samples here in our history, we don't actually want to take the pixel here. We want to take the new pixel from here in the image, but we actually want to take the old pixel from over here where that was there. Philadelphia says, why do pixels flicker when triangles meet? It's because the triangles are going to be snapped to a pixel. Like when you have the edge of the triangle, it's either gonna be drawn on pixels or it's on a pixel or it's not. So effectively, this nice smooth edge of the triangle gets sort of snapped to the nearby pixels. That's why we get flickering there, because as the edge moves, it's gonna snap to different pixels. So yeah, what you want to do then when you're accumulating this is if you have a notion of how that object actually moves since the last frame, which a lot of renderers actually do, we call those velocity, or we call that a velocity buffer. So if every pixel on the image, we also had a corresponding image that was colored by where this was last time in the frame. So like some way of describing that this sphere has moved this much. So if you had that, like this vector here described at every one of these pixels. Then what you can do is you can actually look back. So you can say, okay, I'm going to look at this edge and actually, oh, there's all these motion vectors pointing this way. Well, then I'm going to look the opposite direction and pull my pixel from there. That works actually pretty well. You do have a problem on screen borders, as Alcama mentions, because sometimes you can't look that far. So you also have an issue with what if there was some background information here? Or well, actually, it's this case. You have some background pixels here, but now suddenly all this whole area is background where the sphere was. Where do you get the history for that? You don't actually have it anywhere because it was behind some objects. So you have like, it's the same case also where you have some background pixels here, but now the sphere is there, so you don't have all those, like the correct history. So you try to pull it from over here, but sometimes you don't have that. So there's a lot of issues with this. And generally what we kind of accept when that happens is we say, okay, well then this new area is going to be aliased for a couple frames, but in a couple frames we'll work it out and it'll get better over time. And that's just kind of what we accept. The point I'm trying to make here is that we have a lot of problems with this technique, and we're going to do a lot of hacks to kind of get around that. And a lot of these hacks are already described because this is a pretty well-known technique by now and a pretty widely used one. So there's a lot of ways to get around this ghosting. This one does it by something called neighborhood clamping, and I will totally show the code to do that. In fact, actually, I think what I want to do here is I want to go through and talk about our implementation so far. Big spoiler that shouldn't actually be a spoiler. Our implementation's not done because there's a lot of deep things with just this technique. Like you don't just jitter and accumulate. You also need motion vectors for things, which right now I'm just relying on motion vectors from camera movement, and that's it. And that actually, so the big reason I never looked into this before was that I didn't want to have to do motion vectors for everything, especially if we have like a lot of particle effects or we do some morphing geometry. I didn't want to try to figure that out, but it was brought to my attention at revision this year, and this never occurred to me, that if you just have motion vectors from camera movement, it's actually not that bad. And now I'm actually convinced that that's the case, but a few weeks ago I wasn't. Anyway, so the first thing I actually want to do is I want to show what this looks like without FXAA. And then I want to go through and kind of start talking about the TAA that we have so far. I want to show you guys what it looks like right now. Actually, before I do that, I want to show a couple other problem cases in the demo, just to show you again what the problem is we're trying to solve, and then I'll show you with the TAA and show you how well it works so far, and then I'll show you also the problems that we have so far that I'm working on solutions for. So hopefully this will be kind of informative to see like a halfway done solution, which is kind of what I feel like is missing a lot with TAA, because if you look for TAA, you'll find a lot of presentations. There's a really good one from SIGGRAPH 2016, actually a couple that are really good about like how to kind of set it up, because you want to set it up with a static scene first, and then you want to start doing like the neighborhood clamping and the motion vectors and all that stuff, all the reprojection. And you kind of need to build it piecewise, and there's little bits here and there that you kind of have to pull together when you're doing this. There's like, I haven't found very many good complete code examples of how to do this, and I'm kind of learning as I go as well. So I'm hoping to kind of share, here's where we're at currently after about a week, and it's going to take a bit longer than that because we have a lot of post passes that are going to be really not do well with that reprojection. I'll show you what I mean later. Weird Constructor says, does all that rely on basic OpenGL mesh rendering with shaders? Yes, in this demo, it's all just GL, not super magical. So this scene as well with the Venus has a lot of aliasing problems here. Especially look at some of these edges. Lots of flickering, lots of moving around. And this again has to do with edges kind of coming in and out of pixels. A lot of stuff. And some of this geometry is so thin that even with TAA, as we'll see in a minute, not all of this is going to be fixed. Like we can't actually render all of this with how thin this geometry is. And I mean, that's annoying, but that's just something we're going to have to accept. And a couple other shots back here with these particles. You notice it really bad when you have this under DOF, because like here we have these really tiny particles that end up being like subpixels, and they just flicker like hell as the highlights in them come in and out. And then the depth of field is applied, which kind of expands the problem, so you get a lot of flickering here as well. G Superland, is there an AA solution for such thin geometry elements? Yeah, multi-sampling. But that's a slow one. Here as well, it flickers a lot on these really thin edges. I mean, there's a lot of places. This one, it really bugs me. I think this is one of the more annoying ones. You have these ones in the background where the bokeh is really bright, and this just flickers. All of this stuff is because of aliasing. And yeah, motion vectors can also do motion blur, which is why a lot of engines already kind of had this when TAA was starting to become popular. But that actually, motion blur is another problem when you have anti-aliasing, and I'll get to why. When we start blurring edges, that causes a lot of problems with a lot of the post effects that rely on hard edges. Weird Constructor says, I thought the flickering is on purpose. Some of the flickering in that scene actually is. The flickering on the head itself, here, this flickers a little bit, and that's on purpose. But the highlights in the background are not. And maybe that helps it look nice, but or at least look cohesive, but no, that is not intentional at all. That's just the artifact of the rendering. Pro Science said, if you're just working with triangles, it shouldn't be that hard to calculate the coverage of a pixel analytically. I mean, could you do that for every pixel everywhere, and then you need your shading to play nicely with that? And I don't think it sounds very nice. Yeah, 4K as well. You don't need as much AA just because your eye can't see the individual pixels, but then you still have flickering. You still have a lot of issues temporally, because you still probably will, or at least if you have details that are going to be smaller than a pixel, which you will with a lot of these sharp specular highlights, you should still have temporal issues, even though you don't have like as much of the. You might not notice jagged edges, but as things move over time, you'll probably still get aliasing. Yeah, so that's kind of the problem. Now let me show you this one more time without any anti-aliasing. And we're just going to do this. We're going to not draw this, and we're going to do this. And I think that just works. Yeah, this is the not anti-alias image. It still has a lot of the post effects on it, so it's not going to be perfectly alias, but here you can see also the flickering is a lot worse. And you get a lot of hard edges of triangles. So the FXAA is doing some work for us, but not nearly enough. And again, a lot of this stuff is made worse if we have a lot of shiny stuff, a lot of thin geometry, just because we're gonna hit those problems a lot more often here as well. Lots of little issues. So let me now check out the TAA branch. And I gotta reload the project now. Okay, so this is the TAA solution so far. And it's not perfect, it's not finished, but let me just show you. This is a lot better. You can see the image is a lot more stable. Like, here you don't see hardly any flickering. There's some flickering here from the geometry, which is now noticeable because there's no flickering here. No flickering here. Oh, it's so much nicer. Still a bit of flickering here and there, but I mean, you have to look for it now. Like, look how smooth this is. It's pretty sick, actually. I'm generally pretty happy with it so far. So those of you guys that haven't done TAA, look into it. Where Constructor points out, not as shiny anymore. You're absolutely right. That's actually one of the problems that I'll talk about in a minute. It also is softer, so you can see it handles a lot of this thinner geometry nicely. These edges don't flicker anymore. A bit soft. I might try to do some sharpening on this as well. But like, this is still some flickering, but a lot more stable. It's at least a lot smoother. Still some down here, but like, you have to look for it now. That's kind of the thing. There is less shiny, and I will get to that. There's some really interesting reasons why that's the case. But even in like this shot, where this even has a lot of motion, but you can see here a lot of the flickering is reduced. Let me find more where this is moving. Even with the fast motion, like, we end up getting a little bit of ghosting in here, but it doesn't really matter because this effect you just see the motion anyway. But when things are moving slowly with the depth of field is what I want to show. Where's it good? A bit hard to get really good shots of this, but my point is that if I can find one, I think I want to do this and get it to explode a lot and then go down here. You can see this is a lot more stable. A lot more stable. Yeah, that's exactly it, Philadelphia. It's a lot easier to kind of focus on the effects because your eye is normally drawn to like flickering. Like, that's I mean, at a really like primal level, something twitching is probably something alive that you want to eat. I don't know if that's actually why we're so interested in flickering, but there's a reason why police cars have lights. Like, we pay attention to flickering. So you kind of can't ignore a lot of these artifacts. And I can tell you that our intro is not the only one in this compo that had way too much aliasing. But like here, it's a lot cleaner. Rear Constructor makes a really good point. You can see the sun reflecting on a tiger's eye in the jungle. That's a really good example. Water shiny important. Totally. Here as well, these are totally stable now. No flicker at all. Maybe a tiny bit in some places. And there is flicker still in a couple places, but most of the issues are gone now. But there are definitely still some issues. And so, as a couple of you guys pointed out, it is less shiny now. And that's because the TAA is essentially eating a lot of the highlights that were there before. So that's one of the problems. There's actually a way I can disable that. Let me show you what that looks like. Because we're doing this Luma weighting thing that I want to talk about in a minute. Let's see. So this implementation, first of all, it's not even a finished implementation of TAA because there's a lot of issues there. And I want to kind of disable some of the fixes that we have so I can show you, we can sort of isolate these issues. I was doing some work in the tool, so there's some of that code. But anyway, here, most of this happens in this TAA resolve pass. Which is the thing that's reprojecting the history frame and then gathering some information. So let me disable a couple of the things here. This Ferris weight thing in particular will actually bring a lot of the shininess back. Not all of it, but it will help. So if I save this, then we get a lot of the highlights back. However, it starts to flicker a little more. It's actually not that bad on this scene. So we may keep that, and I might also do some unsharp mask or something to kind of fix that. But like here, that's noticeably more flicker. And this still has TAA, of course, but yeah, like here as well. And I can kind of describe what I've done here. Like I said, there's a lot of details here. This scene as well, you can really tell the difference. Here it's a lot more flickery again. Not as flickery as it was before. It's still a lot better. But it does flicker more with that fix removed. So what that fix does in particular, it's actually talked about in the Unreal slides. But essentially what I'm doing is I mentioned that you accumulate the new frame into the history frame and you're blending like the history frame with the new one. And if you blend that with just like the actual pixel colors, you have a lot of the shiny stuff that is way brighter than anything else that's in the image. And so if you have like one really bright pixel that shows up 1/16 of the time as you're jittering and the other ones are all really dark, even though all the other ones are really dark and that pixel should be mostly dark, you're mostly seeing that really bright one because it like dominates the average. If you average 16 values and one of them is like 100 times higher than the others, it's going to pull up the average so much, like towards the tall one. So what we actually do to get around that is we do this sort of luma weighting thing where we actually transform the color into a space where we kind of weight it with the luma, so we kind of bring all the really bright pixels down into like sort of a flatter image space, flatter color space, and then we do all of the averaging and stuff there, and then we kind of undo that after. But because we undo that after the averaging, we've sort of lost a lot of that brightness. Now a lot of that is somewhat desirable. Like again, it does help with the stability because if I turn that off again and we look at the scene, it's more stable even though we've lost some of those bright highlights. And that's probably something that I might either want to like be able to blend. I'm not entirely sure how I want to solve that yet, but there's some other problems I want to solve first. So that's one of the things that we're applying that should help with stability, but is also kind of hurting the image quality. Let's see, what's something else to talk about? But basically, I kind of actually want to go through this resolve shader without that weighting, so we can kind of. I'm actually going to remove. Whoops. We're going to remove this weighting again, and I'm going to remove a couple other things, and then we're just going to start going through what it takes to render a frame with TAA. Now, I'm not going to remove a lot of the post effects like the depth of field, so we're going to sort of see how those sort of change over time, but I just want to like remove most of the stuff in the TAA resolve pass and just kind of bring it back slowly but surely. So let me just remove stuff here. Yep, that one helps. And then we also don't want to do the neighborhood clamp. Which will actually help the image for now. And then also, actually, let's just go straight up input sample. This is the jittered image. And I also want to do this, do that, and we'll also do this. Lots of little things. Yeah, good enough for now. So what I'm showing here is this is the jittered image. So essentially what we're doing is we have a Halton sequence, and we're going to jitter the entire image. It's a 16 element list of samples from a Halton sequence. And we're going to just, for every frame, we pick one of those, and we just jitter the camera by that much. And we jitter by from negative half a pixel to half a pixel. Like the game Inside, they actually do a whole pixel in either direction, but in this demo, it looked a lot better to just do half a pixel in either direction. So you have like a whole pixel worth of motion that you're jittering over time. And the Halton sequence is a low discrepancy sequence. So it sort of distributes the samples really well. And you hit a lot of the same samples again. So like the things that you're sort of measuring coverage for are going to be represented over and over again, which is what you want. And you also want like individual frames to vary as much as they can between things in the sequence. So this is just the jittered image. And we're not mixing the history at all. So if we go from this, like this is the equivalent of just taking the input sample and then just rendering that. If we then take that and then we mix it with the history sample, so we're just going to take the history sample, which is a sample from this texture, and then we're just going to blend that with the input with something like 0.95 for the blend. When I save this, you'll notice the image just like resolves. And then it looks really good. And we get decent edges here. There's still some flickering here, and a lot of that has to do with the depth of field, which is using essentially a jittered depth buffer with now a smoothed color thing. And so you'll notice also there's some like ghosting with the depth of field, but we're going to ignore that. That's one of the things that I hope to get into today, but actually I've ended up talking so long that I probably won't actually end up doing that, but I'm happy to share this stuff, so that's nice. By the way, Aaron the German said, could you apply some sort of median filter on that? You could do median filter. You could also do like an unsharp mask on the result as well. Like there's a lot of ways to try and fix some of this. But I think one of the things I want to drive home with this is that TAA actually is a lot of hacks, and we're going to see that as soon as I move the camera. So this just takes in the history sample and blends it with the new one. And if we start moving the camera, ghosting occurs. And that's because we're just always taking the history from at the same pixel. And so as objects and the camera moves around, we're blending essentially the wrong history with that sample. So the next thing that we actually want to do is a couple things here. We're going to do something called neighborhood clamping. And this may not actually be the next thing that you want to do, but I found it easier to do that before doing the reprojection because it's actually a little bit simpler. I actually had to change some code in the demo tool to do this. But essentially what we're going to do is we're going to say, well, let's say an object moved like this. And so let's say this, let me do a new example here. Let's say we have an image with a cube over here. And then we're going to look at this pixel. So in this pixel, in this frame, there's the cube there, but let's say the cube moved over here. Now at that same pixel, the cube isn't there anymore. Something else is there, probably background. And so what we're going to do is we want to basically say, well, the history here doesn't seem to match with what our new image is because it's going to have the cube color. So we want to kind of either replace that history and just start with a like non-anti-aliased image. So one of the things that we could do is we could measure if the history and the input differed too much, we could just throw out the history and take the input. That would be okay. What we end up doing, though, is because we don't want that to happen as we sort of jitter around an edge of a triangle. Like we want essentially in a given like pixel neighborhood. So if we look at just a simple neighborhood of 3 by 3 pixels, and let's say the middle one is the pixel that we care about. If we had an edge that was sort of being jittered around this, we don't want to throw away the history every time the edge goes back and forth along this pixel, because then we don't have valuable information about that edge that we're trying to anti-alias. So what we actually do is we sample all of these 9 pixels and we gather sort of in color space, in like red, green, blue color space. We gather sort of a bounding box from like the minimum and the maximum colors that this neighborhood represents. And then we're going to take whatever history we find there and we're going to clamp it inside that neighborhood. So if the history was over here, we're just going to clamp it like here. Again, this is as like an edge kind of moves around, we don't want to reject history that differs a lot from a pixel we may have previously seen, but then still fits within the neighborhood, so that we kind of preserve information around these moving edges. So to do that, there's a couple different things we want to do. So we actually sample a couple things here. There's the Ferris slides have a good example of this. I'm just going to pull those up again. No, where was it? Here? I didn't close these, did I? I think I did, and I shouldn't have. No, I didn't. Here we go. So they talk about this in the Ferris slides. So to get rid of ghosting, they want to do this neighborhood clamping. So you literally look at the 3 by 3 neighborhood, and then you clamp the color within that neighborhood. So to do that in the shader, we would, for example, here I'm going to gather a bunch of this stuff, where I'm just going to read the texture, ignore this color space transform. I'm going to do that in a second, but we literally just sample the texture with an offset. And this is sampling the input texture, of course. And then we're going to accumulate min and max for the colors, which you can see I do here. There's actually 2 patterns in which I sample. This is the 3 by 3 neighborhood. And then this is a little plus sign that's sort of centered around that, because we kind of want that neighborhood to look kind of filtered. So what we actually do is we take the box and we take the plus sign, we sample both for min and max, and then we kind of average that box we get back. I actually think this mix, so this goes like halfway between those 2 boxes, I think this mix should actually be like this parameter should be dynamic, and it should maybe be adjusted by, for example, velocity at the current pixel. I'm not really sure what we would want to do there. But let's just enable this neighborhood clamping. And then as I move the camera, you can see there's a lot less ghosting. It basically solves most of the problem. But if we can find a good example of an edge here, like this edge maybe, they end up being aliased is basically the problem. Actually, they're not too bad in this case because we're still doing the neighborhood clamping. In fact, a lot of the fixes that I'm going to apply here, we're probably not going to see that much difference. But they're in these slides. They're good ideas for a good reason. And if you turn off all the post effects, which I probably should have done for the stream, but I don't really care, then you start to notice, oh, as this edge moves, it isn't as anti-aliased as I would like, that kind of stuff. So that's like the first thing we would do is we sort of clamp the history within the input frame's local neighborhood. And that's really easy to do because you just sample all the pixels around that and accumulate min and max, and then you literally just clamp in color space. This works pretty well. However, one of the issues with clamping is that the picture I drew here is actually wrong. If you were to clamp this into here, you actually get this corner. And what that means is that if the history is often like pretty far outside of the box, it will, like these samples will sort of gather in the corners. So one of the things that you actually want to do is instead of clamping, you actually want to clip to this box. Now I haven't implemented this yet, but it's just essentially a line segment to axis align bounding box clip operation. So it shouldn't be terribly difficult. I'm going to throw this together on Shader Toy before I actually do it. So I'll probably share that. But anyway, so that's another thing that you want to do. And again, this is talked about in the Kara slides. And here even shows artifacts where you get a lot of this like gross red coloring and stuff as the samples sort of clip to the corners. So yeah, so one of the things is trying to shape that, which sort of gives you at least a nicer box. The other thing you can do is instead of doing RGB color space, you can transform that into a color space where one of the axes is luma. And that's a really good idea because then you want to sort of preserve, like if you're clamping color space, you get a lot of, like all of the artifacts that you would get from clamping the color or clipping the color are going to distort the color and the brightness in probably not very predictable ways. Because it's kind of this component-wise thing. But if you orient the box such that one of your axes is luma, then you end up like here. Luma has high local contrast. Chroma typically doesn't. You end up preserving the image better. Is basically all I'm trying to say. Because then when you sort of clamp, you're clamping in the luma range versus the color range. It makes a lot more sense. So that I have done, and that's why I have this RGB to Y COCG, because that's like one of the easiest color space transforms to go from RGB to Y COCG, and then you have that property that one of your axes is luma. Yeah, it's kind of the same as chroma subsampling. It basically, if you were to clamp an RGB space, then you're sort of subsampling in all directions, I guess. If you clamp with a box that's oriented in the luma direction, you're at least only subsampling in. I don't know. It's a bit messy. It's one of those hacks, but it makes sense. But of course, we're still getting more aliasing and a little bit of ghosting as well with this just neighborhood clamp. So then the last thing that I'm going to enable here, I think, is that we actually want to do this reprojection. And so what I do here, I think this is the reprojection here. So the way this reprojection works is we take the UV for the current pixel, and we're going to find the world space position, which in this case, I actually just have in a G buffer. You can also reconstruct this with depth. If you have the clip position X, Y, and then the depth, you can just undo the projection, and then you have view space, and then you can undo the view space, transform, and you have world space. But really what you need is view and projection matrix, because that's represents your camera changing over time. So anyway, I get the world space for the current position, and then I take the last viewport here, which is the matrix that represents the last view and projection transforms from the previous frame. And then I project the world space position into that. And that, after you do a perspective divide and then remap to 0 and 1, actually gives you where that pixel was in the previous frame. So saving that again will actually help quite a bit, because now we're sort of moving along with the edges. I think actually we still get some ghosting here, but Anyway, it's a lot better because then things are actually moving as the camera moves. The last thing I did here, and this is kind of a hack too, is that on edges especially, we get a lot of that ghosting, and where is it here? Actually, it was these slides. This is Lasse Fuglesang, I think you say that. I'm bad at pronouncing Danish names. But this is one of the rendering engineers at Playdid. I think he's at Unity now. Anyway, this is a really great talk, Temporal Reprojection Anti-aliasing Inside, which goes over a lot of these details as well. Essentially, he's got really good slides here. Yeah, if you reproject using just the motion for the current pixel, that might be a jittered pixel, and so you might not be taking sort of the information for that edge along with you. And so you actually want to look at your local neighbor 3x3 neighborhood, and you want to take like the minimum depth, and that should represent like the closest thing that has an edge, and you want to kind of move with whatever that motion vector was. And so that's what this thing's trying to do, is it sort of gathers the nearest depth from the local neighborhood and then reprojects that. And then you can see it also does some little bit of fixing up when it gets the sample position there. And that is mostly what the shader's doing, actually. And with all that together, a lot of the ghosting is fixed. You get really nice edges because it's sort of reprojecting along with that edge. It works out really well, actually. And then the last thing that I wanted to talk about that we're doing in this shader, which is actually taking away a lot of the brightness and something I need to work around, is what I showed earlier with this Ferris weight thing. So this is taken straight up from this Unreal presentation. Essentially, you have, when you're accumulating samples like this, typically what we do in a renderer is we have a lot of buffers that represent like a linear brightness space, and then we do everything with that, with all these linear space, because when you add things together in linear space, then the result is linear and everything works out really nice. But then when we want to display it on screen, we need to do a gamma adjustment. And we also need to take from this HDR linear thing, and we need to get it into low dynamic range, then we need to gamma adjust. That's called tone mapping, is what we do to do that, and there's a lot of really great blog posts about this, especially the filmic stuff. And again, I'm kind of hand-waving over that, but the point is, that's what brings you from a high dynamic range image to a low dynamic range image, and then also gamma corrects it for a monitor display, so that things that look linear, or things that are linear, actually look linear. G Superland, it's a game called Inside. It was the, I guess, spiritual sequel to Limbo, really popular game from like 10 years ago. I think Inside came out 3 years ago, and it's an excellent game, and probably rendering wise is like really kind of a shining light in how games can look. It's got a really nice stylistic look, and it really leans into that, and especially the TAA, which gives it this really nice soft look, just fits so well. So it's really cool. Anyway, when you're accumulating these pixels, there's this question of like, when do you accumulate? Do you accumulate at sort of the end of the chain with where you do everything in HDR, and then at the end you finally accumulate in high dynamic range, or do you do it somewhere else in the pipeline, or do you do it like after you've done your tone mapping, so you get your like gamma corrected pixels and then do that there? And essentially, this is what he's trying to show here, is if you're doing it before your tone mapping, because everything's so HDR, you get a lot of flickering. This might affect other post passes, like, for example, depth of field, where you have like a jittered depth buffer, or motion blur. You'd have jittered motion vectors on top of like a smoothed an image with smooth edges after the anti-aliasing, and then that can smear stuff. But basically what you want to do is you want to get everything into a lower dynamic range, and then do the averaging, and then bring it back to a high dynamic range again. And that's why he's talking about a straightforward tone map solution, because that's what you could do, is you can sort of tone map and then accumulate and then untone map. The problem with tone mapping is that the tone mapping, when it goes from HDR to LDR, it actually desaturates the bright pixels, and this is actually a property that you want with tone mapping, because that's something that your eye kind of does as well. If you look at something really bright, you start to lose a lot of the color information, and when stuff blooms, like you kind of want that to not be as saturated in the brighter parts. It just looks more natural that way. I don't really understand why, but it does. But then if you're going to lose some of that saturation before you do your post passes, that's not good. So this is talking about, like, here he does tone mapping and reverse tone mapping, or tone mapping and then accumulate the reverse tone map, whereas here he does the Luma weighting instead. And so that's what that first thing that I was kind of showing was actually doing with this Ferris weight stuff. This is kind of an annoying thing to have here because that means that this buffer now is accumulating these weighted samples, which means everything that reads it has to undo that. That's why this is in this little separate shader here. But if I enable that again, things don't get as bright, but they get a lot more stable. Anyway, I think that's mostly all the shader itself is doing. And then in terms of the order the post passes, this accumulation, I think the way I have it now is we do the regular like G-buffer rendering. We accumulate all of our lights, and that's all with the jittered HDR stuff. Then we apply screen space reflections, which currently is a pass with the jittered stuff, and that's something else we need to fix, but that's where we're doing it currently. And then I do the TAA accumulation. And after that, then I do bloom, because you want to do that on the smoothed image. I do depth of field on that, which is kind of shit because you end up with a depth buffer from a jittered image on top of a smoothed image. And depth of field really struggles with that because you need, for good depth of field, you want like hard edges in your color buffer that match hard edges in your depth buffer so that you can like reject sharp foreground objects from bleeding onto blurred background objects. And you kind of lose the ability to do that once you've smoothed your edge that by definition has some of the foreground in the background, some of the background in the foreground along that edge. So you're going to end up with these sort of smearing artifacts. And in fact, that's exactly what we see here with the current solution, the way I have it set up. And this is why one of the reasons why this is unfinished. Essentially, this whole scene ends up with this kind of halo around it. And that's exactly what's happening, is that the background is blurred because of the depth of field, and the foreground shouldn't be blurred. Normally, these samples would be rejected by the depth of the field, but because the jitter depth is blurring a blurred image, there's some extra color information that sort of leaks over this edge. So one of the things that we could do there is we could do, for example, depth of field before we do the TA resolve. But then the issue is that for pixels like the ones in this image, where before we had TA, this was flickering a lot. That's because those really bright pixels would kind of come in and out, and then they'd be dilated by the depth of field. And so you'd get some frames where you had this really dilated bright spot, and then other frames where you wouldn't. And that, again, is flickering. So you kind of want to do TAA to the inputs of depth of field, but you also want to do TA on the outputs so that you can do depth of field with a jittered depth buffer and a jittered color buffer, and then have that do edges properly, but then TA the result to kind of remove the little jagged edges. And that's what I wanted to work on today, but I ended up just talking this whole time. There's actually a presentation I think it's called A Life of a Bokeh, which was presented at SIGGRAPH 2018 that talks about doing TAA as inputs to the depth of field. And in fact, the Ferris slides as well mention this too. Just saying that here, temporal A is a firewall. So it's talking about exactly this, where you have this jitter depth, but you're doing it on past TA, where again you're blurring stuff. And so that's one of the reasons why this isn't like a finished solution. I guess the point I'm trying to make here again is that TA is a lot of hacks on hacks, which altogether can really help the image. You guys saw the results. This is a lot smoother. But it's not without its problems. And you can't just kind of suddenly decide to do TA at the end and hope things work out. You really need to kind of carefully decide what you want to do. Like I could, for example, accept this haloing, which is also really apparent in this scene, especially. And then say that, well, I mean, the image is pretty stable. It looks pretty good. Yeah, hacks on hacks, exactly, G. Superland. But for example, I would like to try alternatives for that. And also for the screen space reflections, because those still flicker a lot, because that's, you're essentially moving the reflection ray every time you jitter. And I want the TA to clean up some of that, but there's better ways to do that. So you kind of, when you do TA, you sort of need to start doing temporal accumulation of several different buffers in different parts of your post pipeline. So I think what we'll probably end up with is we'll end up with a temporal resolve on the the reflections in particular, we'll probably end up with a temporal resolve on both of the depth of field inputs, because for our depth of field, we actually separate the image into a near and far field and in focus part, and then we blur the far field and the near field separately so they don't blend into each other. And on both of those near and far field images that we separate, we probably want to do a TAA resolve on those. And you have to be careful with what kind of TAA resolve you do in all these different situations as well, because if you're doing a TAA resolve for reflections, you actually don't want to resolve with the sort of primary hit ray or primary ray hit position. You want to do it with like the secondary one, so that reflections will sort of travel along with their proper motion as things move along the screen, rather than the surface they hit. Otherwise, you smear the reflections. So you need these sort of specially tuned temporal resolve passes on several of your different post passes that all have different constraints. Like like I said, the reflection one needs to track the reflections more so than the actual edges of the objects. In fact, it actually should do a hybrid of both. There's some good papers about that are coming out recently. And like the depth of field one needs to reject things where the circle of confusion is too different, so that you don't get bad bleeding. Because a lot of the times too, with those particular TAA resolves, or temporal resolves, I should call them, because the TAA, like the main TAA pass is meant to do anti-aliasing, but it also really helps with temporal stability. But for all these other ones, like you don't want to anti-alias the depth of field buffers. You just want to have them be temporally stable. So they all kind of have these little different constraints, so you end up with slight variations on the same main reprojection shader. And one of the reasons why I haven't done this on all those yet is because I wanted to nail this main resolve shader first. Now I think I've basically gotten there with this, so now I want to start applying it everywhere. So yeah, so I want to do that with the reflections, so I want to have that do its own resolve before being composited with the image, and then that'll go into the main TAA resolve. And then the depth of field ones I want to do. And I don't really know how that's going to work yet, because these are ongoing areas of research in modern games. Like, what order do you do these? How do you do these? The answer is it depends, and you're just kind of trading off different artifacts. Like for example, the Inside game, I don't think it had depth of field, so they didn't worry about that. And I think they just did TAA at the end of everything, which works really well for their game. And they also have these little like motion blur fallback things in their TAA implementation that I probably won't take, because again, that might cause issues with some of the other post passes. It really depends. And there's also more general problems too, like especially with like motion blur and depth of field. Like, we don't do motion blur in our demos, but if you're doing both, like what order do you do those in? Because both should ideally happen at the same time in an actual camera, but in a game you kind of have to decide. Alcama says, need a tool to inspect the G buffer. And Daniel Collin, hey Daniel Collin, says use RenderDoc. Yes, RenderDoc works with our demos, by the way. I think I might have a capture that was kind of cool of one of these shots. Maybe not. I'm not going to bother actually trying to do that again. It doesn't work with our tool, but it works with the resulting demo, which is kind of cool. But yeah, and the Inside game also like really leans into having that TAA resolve after everything. So they actually introduce a lot of noise into their image, and especially things like eventually I want to do an ambient occlusion implementation, and that is another post effect that works really well with reprojection. So you can have these more noisy effects and actually introduce more noise because you know you're going to do a temporal resolve after, which is one of the reasons why I also experimented with having the reflections composited into the image before the TAA resolve. But I think I'm going to have to be a little more clever than that, do its own resolve and stuff too. So lots of stuff. Ralph124C41, thank you so much for the sub. Appreciate it. So yeah, that's kind of the point I'm trying to drive home with TA, is that it's just one of those things that kind of affects like all of your pipeline a little bit if you really want to do it right. And sometimes you can just afford to cut corners. Like if you just want to use the jitter depth and the blurred color buffer, maybe that's fine for your demo or your game or whatever, and that's totally cool. You'll save yourself a lot of effort doing that. But in this case, I would like to try and fix that, just because we use depth of field a lot, and those ghosting artifacts really bug me. I I think it's really apparent here as well. Like we have these bleeding artifacts here from the depth of field. And also, you probably can't see it on the stream, but this depth of field does still flicker a bit because of the jitter depth. So you want to do like TAA resolves on the input to it to make them temporally stable, but then it's still going to jitter a bit on the output, but then you want the main TAA resolve to kind of fix that as much as it can. But I did do an experiment. I can't really show it here because it takes a minute to hook it up again. But if you do just the full depth of field before the main TAA resolve, then you actually have a lot of problems because like if you have those bright pixels that sometimes are dilated and sometimes aren't, what happens is that looks to the TAA implementation exactly the same way as an object coming in and out of frame would look. So your neighborhood clamp essentially throws out the history whenever that happens, and it can't eliminate any of that flicker, which is really annoying. So some of this we probably can't ever fix entirely, but we should be able to fix a lot of this stuff because a lot of those edges where sometimes they're dilated, sometimes they aren't, I imagine that happens a lot less once you have stable inputs to a depth of field where your jitter depth matches the jittered color. I think that'll end up working out better. Maybe not though. But the SIGGRAPH 2018 presentation, which I guess is a newer version of that Unreal renderer, they talk about doing that and it seems to work well. And then they just will reject history based on like 2 different COC or whatever. And I would really like to play with that, but I guess I won't be able to do that for another couple weeks now because I've been spending all this time talking. Because I can't stream for much longer, maybe 10 minutes longer, actually, to be honest. But anyway, I did want to share. I want to share what this looked like so far. Like I said, I've been playing around with this for about a week, and I'm actually really happy with the results. And I can definitely point you guys, if you guys are interested in playing around with this yourself or learning more about the technique, that inside presentation is extremely good. Actually, both inside presentations are really good. The other one is about adding a lot of noise and dithering to the image to make it a lot more temporally stable and a lot more smooth. That's actually given by Lupit of Hornet for you demo scene people. And also mentions some of the chromatic aberration stuff that we took for Elysian back in the day. So that's kind of fun. That's a really good presentation. Both the inside presentations, especially the anti-aliasing one, obviously. The Ferris slides are really good. There's, I think, the Uncharted 4 slides from SIGGRAPH 2016 go into this a lot. The Bokeh one from SIGGRAPH this year, it's actually nuts how much they're doing for that effect now. And ours will never get that deep, but yeah, a lot of stuff from SIGGRAPH presentations and games tech that we take from this, or that we take and put into these demos. But yeah, eventually I also want to do a nice ambient occlusion implementation. And that as well is going to have probably its own temporal resolve as well. So it's like temporal reprojection on temporal reprojection on temporal reprojection. Here as well, you have the ghosting here that I want to try and fix. Lots of stuff. But yeah, I think it was worth having a stream today. And even though I didn't make any progress, I'm happy to share this stuff. I think it's really interesting. Like I said, I held off on implementing this technique for a long time. I was admittedly late to the party discovering temporal stuff like this. I mean, this was in games for a long time and in demos for a long time as well. And like I knew about it when I started building our new rendering tech for Elysian back in 2016. But I just knew it was going to be a pain in the ass. And I also didn't realize that you could get away with just the camera motion for motion vectors for most of it. So that also really made me hold off. And then, of course, as our renderer progressed, we had more complicated depth of field and everything, then I really didn't want to do it. But yeah, people telling me at revision that you could do it with just the camera motion vectors was really kind of the kick that I needed. And also just how much painful aliasing we had in this demo. I've been considering, once I fix all this stuff, releasing a final with TAA, but I'm not actually sure if I want to, because if it ends up looking too different, like some of the stuff does look less shiny, then I kind of don't want to do that if we end up changing the look too much. And then, like, I'm doing most of this development for the next demo anyway, so I don't really care if if we don't end up like releasing a final with these bugs fixed, because the demo won. Like I'm happy with it, and I'm happy with what we put out, and just want to improve this for my own exploration, and then using the most recent demo makes the most sense because it's the most content, it's the most recent content, so it makes sense to try and like use this as test content, because that's the other thing that happens when you're doing a game or doing a demo is like when you start experimenting with this stuff, you need test content to be able to test these filters. So but yeah, this technique has been on my radar for a long time, but it took me a long time to actually sit down and start working on it, and I'm pretty happy so far. Yeah, that's probably true, Daniel Colin. Camera stand still and have objects flying towards the camera would definitely break. What a lot of people do is they adjust this resolve parameter, so like how much they mix the history with the input pixel, and you would do that depending on the scene. Because essentially what you're trading off there is your response to motion versus how much anti-aliasing you have. So if you want it to respond better to motion, like faster, but you can accept a bit more aliasing, then you would turn that lower, so that the history would account for less of the new color. Whereas if you want more aliasing in slow motion, then you want higher value. In our demos, I tend to really not like a lot of motion, actually. Like obviously I want everything to move in the scene, but like especially fast moving stuff I generally don't like the look of, and especially fast moving cameras I'm just not that big of a fan of. So in our demos, like this solution works really well, and I think it's going to continue to work in our future demos because I don't think that's going to change. So I would say that's definitely something that we should have been doing for a long time. But yeah, it definitely does depend, and there's a lot of these hacks too that like sometimes you want to adjust your neighborhood clamp. Like I think a lot of the earlier versions of these filters were doing, like if you look at your 3x3 neighborhood for the neighborhood clamping, I think they would like change the size of that neighborhood based on velocity. So like some velocity weighting and stuff, and a lot of those kind of ideas I think are pretty good, but really depends. It's yeah, exactly, John Colin. It's a pain in the ass for motion vectors and a lot of other stuff. Like it's just frustrating. Yeah, exactly, Alcama. That's the velocity weighting. Combine composition of history to current, the amount of movement. Exactly. Yeah, very easy to break it. and like, for example, one of the things that this demo doesn't have any of is scrolling textures, which is like anything that has scrolling motion in it is really bad unless your motion vectors also account for that. So a lot of the times you kind of need to hack in motion vectors for things that aren't actually moving, but like that you kind of know are moving. And this stuff just eats shit with that. Actually, I find that particularly bad in Mirror's Edge Catalyst. Not to call out that game. I think it's an awesome game. I'm actually wearing a shirt about it right now. But there are several cases there where there are scrolling textures, like techie looking stuff, and under TAA, they just streak really hard. And that, me calling out that game is not saying that that's a shitty game. My point is that, big game studios deal with this as a problem. Like there aren't really perfect solutions to this, because again, like your neighborhood clamping, if it just sees different pixels, maybe that's something changing for that pixel, and that's an important part of history, or maybe it's a new object is there. You don't know when you just have that view of the world. So yeah, it's pretty nasty. Yeah, exactly. Velocity. Have to say, okay, this part of the scrolling texture was over here, but then maybe that doesn't align with the stuff that's under it. And then transparency is a whole bag of worms, like, or a whole can of worms. Like transparency is already a problem if you're doing a deferred renderer. Then you would often need to like composite the transparent stuff on top of that stuff in different passes. It really sucks. Things like depth of field suck with transparency. Temporal stuff also very much sucks with transparency, because you kind of have to like decide how much of the stuff that's behind the transparent object to take in for history and how much for the surface itself. If we had several different layers of motion vectors, like if you did some kind of like depth peeling for your motion vectors, that might help, but then you would also need like different history buffers for the different parts of the color. Like, my solution to that is don't bother. It gets really nasty. That's the whole thing. But again, like, you'll notice there was no transparent stuff in this demo, not even for the particles, or in the last one we did, and that's very much deliberate because we don't have a good solution for that. We have a deferred render and we're just sticking to it, and so just doing solid geometry. The other thing with like shadows as well for a lot of these particle effects, like the head here, shadows just work if it's all opaque geometry, so just do that. If you have that much VRAM and 16 times the compute, SSA is a great idea. Don't think you'll have that though. Actually, 256 times the compute. That's what you need for that. Gets pretty crazy. That's my whole point. It's just that like these are kind of ongoing areas of research in games right now. And by extension, demos. So it's the name of the game is not finding the perfect solution. It's finding the right solution, the good enough one, and accepting what you can accept. Like this image, for example, like there's flickering here with the reflections, but it still looks way better than it did before. And even though we don't have proper motion vectors for these particles, and like we don't need them, this still looks good. Even though there might be some streaking or whatever for an image, this effect runs pretty fast. It works well. So like I don't think I need motion vectors, but maybe for a feature demo we might. Right now just doing the camera is good enough. So that's one way we're going to cut a corner. But then the haloing for the depth of field really bugs me, so I really want to fix that. Focusing the efforts where they actually happen for your content. And right now this is the content we have, so I'm going to tweak it till this for this, and then later when we do our next demo, maybe we have the totally wrong solution, but it's probably going to be good enough. So Superland, if you have a text LCD display, you're probably getting a bit of TAA on that already. At least you're getting some accumulation over multiple frames, but you're not going to get any of the reprojection and or neighborhood clamping or any of that stuff. But yeah, I actually have a list here. That's probably worth sharing when I'm talking about the implementation here. I have a list of the things that I've done so far and like what I was thinking, kind of things I implemented while working on this. Where is it? I have way too many things open here. Because that was actually one of the things, to get the previous frames camera matrix, its view and projection matrices, I actually had to extend the demo tool to make sure that our operator grid actually supported a way to save and restore like variables that persist between frames. That was a feature that we didn't have. And I didn't want to just make every variable persist, because I think that's something that you need to decide if you're doing or not, because you can cause a lot of problems with lingering state in an operator graph like this. So I just decided that like I'm going to make a specific like store, so it's database style, like you either store into it explicitly or you load it explicitly. You never get that for free, and that way you're only using it in very few places. So had to go deep into the tool to fix that. Yeah, exactly. Superland in demo Redis. But yeah, so here we did the initial one where it's just like remove all the post effects to test stuff and then just add the jitter, and then just do the resolve, because to get it on a static image is really easy. And then when you have that, you kind of have like a ground truth, like this is what it should look like. And then you do the neighborhood clamp. Here I did the simple clamp, better min-max calc with the plus sign versus the through or through neighborhood. This is the orient the box in a space where one of the directions is Luma, and as you can see, I haven't done proper clip against the box either. The inside talk actually talks about a nice approximation to this, where you don't actually clip exactly where your line segment does. They actually always just clip towards the center of the box, which seems pretty good. Maybe I'll steal that, but I want to do a proper one, see how bad it is first. Implement jitter for all the scenes. I ended up doing this as a jitter shear thing. I just added a expression type in my tool that was shear projection, where you give it a projection matrix and an X and Y shear, and then it will just do that in the right components. That was easier than making like actual indexers in the operator grid, because we're kind of limited. I've shown this a few times, but we have this operator grid, and like this has variables and stuff, but it doesn't have like array indexers or fancy things, because you generally don't need them. So we kind of have to adjust that runtime. That's effectively what it is. It's a VM for doing demo stuff. And sometimes it's missing features, but most of the time it has what we need. So sometimes I extend it with specific stuff like that. And then here I did hybrid tone mapping luma weight approach. This was the Keras weighting stuff. I might do that motion stuff. Didn't end up doing proper motion vectors, just did the persistent variables and did the camera stuff. Pretty happy with that. Proper jitter pattern. So initially I did like a grid jitter pattern, which is easier to start out with, but then I implemented 16 element Halton sequence. And then I started bringing back the post effects, just writing down notes. Like here I introduced SSR before that, but there's a big issue. It's pretty unstable. So I need to come up with something there. I did the field as well. Have to revisit, rethink it. Bloom's really easy. You just want to do the after TA. We have this fisheye effect, which is here, and now this edge is aliased, because before we just had FXAA on the end of everything. So if we introduced like a hard edge like this, then it would just get eaten by the FXAA. So here I need to do like some feathering or something. Introduce the glitch. It's alias now, but I actually kind of like that, so we're gonna stick with that. And then yeah, I want to parameterize the resolve mix, as I mentioned earlier, so we can change that per scene. So for example, this scene in particular would probably have a lower mix to make the motion show a little bit better, even though these slower parts look really nice. So I'm pretty happy with that. And then I also end up actually doing a copy of the resolve buffer. So I resolve from one into another and then copy back. Whereas since we have the persistent variables, and actually I added a frame counting in the demo tool as well, that we should actually be able to do proper ping pong with that. So just the list of things that I ended up doing. Anyway, I'm having a lot of fun implementing this. Probably won't be able to touch it for a couple weeks because I'm going on vacation. I'm going to head out unless you guys have any specific questions about this. I'm a little bit disappointed that I didn't get to start working on trying to fix the depth of field, but at least I can kind of share what I'm thinking. And I think it's kind of cool to see like the half-finished solution here. And I would like to at least cover a lot of this stuff in a blog post later, but I'm not going to write anything until stuff actually works better. And again, I'm also not trying to find like the perfect solution. It's still going to flicker a little bit. It's not going to be perfect, but it's going to be a lot better. So I'm pretty happy about exploring this. Special thanks to Coupe and Kuzma, who were the guys who told me that you actually could do this with just the camera motion vectors. It's probably going to be okay. I think this proves that, at least for our content, they're absolutely right. The way Coupe told me that is he actually threatened to use our demo as a bad example for aliasing in a presentation if we didn't fix it, which unfortunately is a thing that I respond to. So here I am fixing this. But I am pretty happy actually that this is working out so well, and it's been fun. So greetings and fuckings to him for that. At least now, if he does that, he'll have a nice version as well to show, which I think he would do. I think it'd be unfair to use it as a bad example if we also fixed it. To be honest, I think he's just happy to see this, or at least we'll be happy to see a better version. Anyway, yeah, glad you guys like that. At least I have a lot of fun talking about this. Probably won't. I mean, I'll stream when I get back, and then maybe we'll work on this. Maybe I'll work on fixing the depth of field stuff then. And I don't know, like that's probably going to take some experimentation, so that might be fun to do. Anyway, I got to go. Thanks, guys, again for hanging out, and I'll see you next time.